Welcome to the Deep Sleep Science Channel. Settle in, relax, and let your breathing slow down as we gently explore one of the most powerful and fascinating natural forces on Earth, volcanoes. If you enjoy calm journeys through science like this, you might like to tap the like button, subscribe, or leave a comment before sleep quietly finds you. Volcanoes are openings in Earth's crust where molten rock, called magma, rises from deep within the planet and eventually reaches the surface. When that molten rock emerges into the open air or water, we call it lava. In a way, a volcano is like a natural vent that allows the heat and material from Earth's interior to escape slowly over time. Without volcanoes, our planet would trap much more heat inside, and its surface would look very different. Most volcanoes are created by the slow movement of Earth's tectonic plates. These plates are enormous pieces of the planet's outer shell that drift slowly across the surface. Sometimes the plates pull apart, allowing magma to rise through the gap. Other times, one plate slides beneath another in a process called subduction, melting rock deep below and feeding chains of volcanoes above. In rare cases, volcanoes form above powerful hotspots deep inside the mantle, where unusually hot material rises from far below the crust. Volcanoes can appear in many different shapes. Some are tall and steep mountains built from layers of ash and lava, while others are enormous, gently sloping shields formed by countless flowing lava eruptions. There are even small volcanoes that can appear in just days when fragments of lava pile up around a vent. Over time, eruptions, collapses, and erosion shape these volcanic landscapes into some of the most dramatic scenery on Earth. What makes volcanoes dangerous is not only the lava that people often imagine. Some eruptions release huge clouds of ash that can darken the sky and travel thousands of kilometers. Others produce pyroclastic flows, fast-moving currents of hot gas and ash that rush down slopes at incredible speeds. Volcanoes can also trigger mud flows called lahars, release harmful gases, collapse entire mountainsides, or even influence global climate if enough material reaches high into the atmosphere. Despite these dangers, volcanoes are also incredibly important for the planet. Much of Earth's land was built through volcanic activity over millions of years. Volcanic soils are often very fertile, supporting farms and communities in many regions. The heat beneath volcanoes can also provide geothermal energy, helping power homes and cities. The greatest concentration of volcanoes on Earth lies around the Pacific Ocean in a massive zone called the Ring of Fire. This region stretches through countries like Japan, Indonesia, the Philippines, Chile, Alaska, and parts of the western United States. It exists because many tectonic plates meet and interact there, creating perfect conditions for volcanic activity. And one of the most surprising facts about volcanoes is that most of them are actually hidden beneath the ocean. Thousands of underwater volcanoes quietly build the seafloor along mid-ocean ridges, where new crust is formed every day. These eruptions rarely reach the surface, yet they are constantly reshaping the planet below the waves. Volcanoes are also not unique to Earth. Massive volcanic mountains exist on Mars, including Olympus Mons, the largest volcano in the entire solar system. On Jupiter's moon Io, volcanic eruptions happen so frequently that the entire surface is constantly being renewed by lava. These distant worlds remind us that volcanism is a powerful planetary process that reaches far beyond our own planet. So tonight, as we slowly drift through these fascinating facts, we'll explore how volcanoes form, how they erupt, and how they quietly shape the world beneath our feet. And as you listen, imagine the deep earth slowly breathing, sending warmth, rock, and energy upward through these ancient openings in the crust while the rest of the world gently drifts into sleep. Taken as a whole, volcanoes are not simply mountains that erupt from time to time. They are vast natural systems that connect the deep earth, the atmosphere, the oceans, living ecosystems, human communities, and even the geology of other worlds. When we look at a volcano, we are really looking at one part of a much larger planetary conversation. Mars is home to Olympus Mons, the largest volcano in the entire solar system. It is so enormous that it makes even Earth's biggest volcanoes seem modest by comparison. Its existence shows that volcanic activity is not just an Earth story, but a process that shapes worlds across space. Olympus Mons is a shield volcano, which means it has a broad, gently sloping form like the great volcanoes of Hawaii, but on a vastly larger scale. This shape tells scientists that much of its lava was able to flow far and widely before cooling. Even on another planet, the same basic volcanic patterns can appear in familiar forms. Olympus Mons rises more than 20 kilometers above the surrounding plains, depending on how it is measured. That extraordinary height is difficult to picture because it towers so far above its landscape that it dwarfs many mountains we know on Earth. It is one of the clearest reminders that volcanic construction can create some of the tallest features on any planetary surface. Jupiter's moon Io is the most volcanically active body known in the solar system. Its surface is constantly being reshaped by eruptions, lava, and heat from within. In a way, Io shows volcanism at its most restless and continuous. Io's volcanism is driven mainly by tidal heating, rather than by plate tectonics or ordinary mantle plumes. As Io is squeezed and stretched by Jupiter's gravity and the gravity of nearby moons, its interior heats up, and that heat fuels volcanic activity. It is a beautiful example of how worlds can stay geologically alive for very different reasons. The 1815 eruption of Tambora in Indonesia was one of the most powerful eruptions in recorded history. It was so immense that its effects were felt far beyond the island where it occurred. Tambora is often remembered as one of the clearest examples of how a single volcano can influence the whole planet. Tambora's eruption began with smaller activity before a catastrophic climax on April 10th, 1815. This pattern matters because it shows that even an event of enormous scale can build toward its most destructive phase. The mountain did not transform all at once, but escalated into one of history's greatest eruptions. The eruption of Tambora removed much of the mountain's summit and left behind a large caldera. In simple terms, the volcano changed its own shape dramatically, collapsing inward after so much material had been expelled. It is a reminder that eruptions can rearrange entire landscapes in a short span of time. Tambora's eruption sent huge amounts of ash and sulfur-bearing material high into the atmosphere. Once volcanic material rises that high, it can spread far from its source and remain aloft for a long time. That is one reason some eruptions reach beyond local destruction and begin affecting global systems. The atmospheric effect of Tambora helped create the climate anomaly known as the year without a summer in 1816. Temperatures were disrupted, weather patterns shifted, and many places experienced unusual cold and failed harvests. A volcano in Indonesia was able to leave fingerprints on seasons half a world away. Crop failures and strange weather connected to Tambora's aftermath affected regions far from Indonesia. This is one of the clearest demonstrations that volcanic eruptions can matter not only to nearby towns, but to food supplies and daily life across continents. Volcanoes can sometimes influence human history on a global scale. The 1991 eruption of Pinatubo in the Philippines was one of the largest eruptions of the 20th century. It was powerful enough to become a major scientific event as well as a humanitarian one. Pinatubo is often studied because it showed both the danger of volcanoes and the importance of careful monitoring. Pinatubo released so much sulfur dioxide into the atmosphere that it temporarily cooled the global climate. This happened because volcanic aerosols reflected part of the sun's energy back into space. It is a remarkable fact that a volcano can, for a time, slightly change the temperature of the whole planet. The 1883 eruption of Krakatau is another famous example of an eruption with worldwide atmospheric effects. Its blast, ash, and aftermath became known around the world and entered both scientific records and public memory. Krakatau remains one of the classic examples of a volcano whose influence spread far beyond its immediate region. The 1883 Krakatau eruption also produced tsunamis that killed many people in coastal communities. This shows that volcanoes are not only about lava and ash, they can also disturb the sea in devastating ways. A volcano can create hazards across land, air, and water all at once. A supereruption is an extremely large explosive eruption, generally associated with the highest category on the Volcanic Explosivity Index, VE8. These events are rare on human timescales, but they represent the upper end of what volcanic systems can do. They are among the most powerful natural events known on Earth. Supereruptions are rare in relation to everyday human history, yet they have had major effects over the long history of the planet. Their rarity can make them seem almost unreal, but geology preserves their evidence clearly. They remind us that Earth's quiet surface sits above processes capable of immense change. Large caldera-forming eruptions can eject tremendous amounts of ash and pumice over huge areas. In such eruptions, the amount of material thrown out can be so great that the volcano's structure itself becomes unstable. These are not just eruptions from a mountain, they are landscape-changing events. Most volcanoes form where tectonic plates move apart, collide, or where unusually hot material rises from deep within the mantle beneath a plate. This means volcanoes are closely tied to the great engine of plate tectonics and to the movement of Earth's outer shell. They are part of the way the planet releases heat and reshapes itself over time. The majority of Earth's volcanic activity happens underwater rather than on land. So even though famous volcanic mountains capture our imagination, most volcanism is hidden beneath the oceans. In that quiet darkness, new crust is constantly being created and altered. Most submarine eruptions occur along mid-ocean ridges, where new ocean crust forms as plates move apart. These long undersea mountain chains are among the most active volcanic regions on the planet. They help build the seafloor in a slow but continuous process. Many underwater eruptions happen too deep to be seen directly from the surface. That means some of Earth's most common volcanic activity takes place almost entirely out of sight. The planet is far more volcanically busy than everyday experience might suggest. Volcanoes also exist on other worlds, showing that volcanism is one of the fundamental ways planets and moons release internal heat. Earth is not unique in having fiery geology. Across the solar system, volcanoes help reveal what is happening deep inside distant bodies. Studying volcanoes on other worlds helps scientists understand how heat escapes from planetary interiors. When researchers compare Earth, Mars, Venus, and Io, they learn that volcanism can take different forms under different conditions. In that sense, volcanoes are windows into the hidden workings of planets. On Earth, volcanism has helped build continents, ocean crust, islands, mineral deposits, and changes in the atmosphere across deep time. Volcanoes have not just destroyed landscapes, they have also created them. Much of the ground beneath us exists, directly or indirectly, because of ancient volcanic processes. Early Earth was probably much more volcanically active than the modern planet. In its younger years, the planet held more heat inside, and that heat likely escaped through far more frequent volcanic activity. The Earth we know today was shaped in part by that much more fiery beginning. Volcanic outgassing contributed important gases to Earth's early atmosphere. Over long spans of time, gases released from the interior helped build parts of the air surrounding the planet. In that sense, volcanoes helped set the stage for the world in which life later developed. The long-term carbon cycle includes volcanic release of carbon dioxide, balanced over geologic time by processes such as weathering and sedimentation that remove carbon again. Volcanoes are part of a deep planetary rhythm rather than a one-way process. They participate in cycles that link rock, air, water, and time. Over geologic time, volcanism has been both a creator and a destroyer of habitats. Eruptions can bury forests or coastlines, yet volcanic land can later become soil, islands, reefs, and new ecological space. The same process that removes one environment may open the door for another. Volcanoes are not rare exceptions in Earth history. They are one of the main ways the planet reshapes its surface and releases internal heat. Seen over millions of years, volcanism is not an interruption of the normal Earth, it is one of the normal Earth's defining processes. A quiet volcano can still remain active beneath the surface, with fluids circulating, gases escaping, and rock slowly deforming. Silence on the outside does not always mean stillness below. Many volcanic systems continue changing even during long, peaceful intervals. A volcano can be active, dormant, or extinct. But these categories are not always simple or permanent. A volcano that seems quiet for a very long time may still erupt again if magma, gas, and pressure conditions return. That is why scientists use these labels carefully. At any given time, dozens of volcanoes around the world are in continuing eruption status. This means Earth is not waiting quietly for rare volcanic moments. It is already expressing them somewhere, almost all the time. The planet is more continuously active than many people realize. On a typical day, around 20 volcanoes may be actively erupting somewhere on Earth. Some are sending ash into the air, others are pouring lava, and some are quietly degassing. Volcanic activity is not a rare annual event, but an ongoing global reality. The Smithsonian Global Volcanism Program tracks Holocene volcanoes, meaning volcanoes that have been active during roughly the last 12,000 years. This time window matters because it focuses on volcanoes relevant to the modern Earth and recent human history. It helps scientists organize volcanic records in a meaningful way. The Global Volcanism Program database contains more than 1,000 volcanoes with Holocene eruptions. That number alone shows how widespread volcanism has been in relatively recent geological time. Earth's volcanic landscape is broad, varied, and truly global. Iceland is one of the world's most volcanically active countries because it sits both on a mid-ocean ridge and above a hotspot. That combination gives it an unusual concentration of volcanic energy. It is one of the clearest places on Earth where two major volcanic influences meet. Hawaii is built mainly by shield volcanoes formed over a hotspot in the Pacific Plate. Over long periods, repeated eruptions have constructed entire islands from lava rising from deep within the Earth. The Hawaiian Islands are, in a very real sense, large volcanic monuments built layer by layer. Kilauea is one of the most active volcanoes on Earth. It has become one of the best-known volcanoes because it has erupted frequently and has been studied in great detail. Its ongoing activity gives scientists a valuable chance to watch volcanic processes in real time. Much of Kilauea's surface is geologically young because repeated eruptions keep covering older ground with fresh lava. In volcanic terms, this means the landscape is constantly being renewed. A place can look ancient, and yet in geological age, be surprisingly new. Mauna Loa is one of the largest volcanoes on Earth by volume and area. Its true immensity is easy to underestimate because its broad slopes rise so gradually. It is a mountain of huge scale, built quietly over time by many eruptions of fluid lava. Mauna Kea rises so high from the seafloor that, measured from base to summit, it exceeds the height of Mount Everest above sea level. This does not make it the tallest mountain above sea level, but it does reveal how enormous volcanic mountains can be when their underwater foundations are included. Much of volcanic grandeur lies hidden beneath the ocean. The Andes contain many stratovolcanoes formed by subduction, where oceanic crust sinks beneath South America. This great mountain chain is not only a line of peaks, but also a product of deep tectonic interaction. Volcanoes there are part of a long continental margin shaped by plate collision. Volcanic arcs can be continental, like the Andes and Cascades, or oceanic, like the Aleutians and Marianas. In both cases, they often form sweeping chains related to subduction. These arcs are some of the most important volcanic belts on Earth. The Aleutian Arc contains many volcanoes aligned in a broad curve created by plate subduction. Its shape reflects the geometry of the sinking plate below. Even the map pattern of volcanoes can reveal what the deep Earth is doing. Arc volcanoes often form in curved chains because of the way one tectonic plate bends and descends beneath another. The shape is not random. It is a surface expression of deep structure below the crust. The United States has more than 160 active and potentially active volcanoes monitored by scientists. That number surprises many people, because volcanoes are often associated with only a few famous peaks. In reality, the country contains a large and varied volcanic landscape. Most of the active and potentially active volcanoes in the United States are in Alaska. That is because Alaska sits along a highly active subduction zone where one plate moves beneath another. Its remote setting hides one of the busiest volcanic regions in North America. Alaska experiences eruptions almost every year because of its place along that active plate boundary. Many of these eruptions occur far from large cities, but they still matter greatly, especially for aviation and regional hazards. It is a reminder that volcanic activity can be frequent even where few people live nearby. The Cascade Range in the western United States includes volcanoes such as Mount St. Helens, Mount Rainier, and Mount Shasta. These peaks are part of a larger tectonic system, not isolated mountains. Together they form one of the best-known continental volcanic arcs in the world. Mount Rainier is considered particularly hazardous because large populations live downstream in valleys that could carry lahars far from the volcano. The danger is not only on the mountain itself. Water-rich volcanic debris can travel long distances and reach communities well beyond the summit. Yellowstone is famous for its geothermal features and also contains a large volcanic caldera system. Many visitors know it for geysers and hot springs, yet those surface features are connected to a much deeper volcanic story. It is one of the most famous examples of how volcanism can shape a landscape without constant lava eruptions. Crater Lake in Oregon fills the caldera formed after the collapse of Mount Mazama. What is now a calm, deep blue lake is actually the result of a massive volcanic event in the past. It is a peaceful modern landscape resting inside the remnant of a dramatic, ancient eruption. Most volcanoes form in places where Earth's outer shell is already under stress. This usually happens where tectonic plates are pulling apart, pushing together, or where unusually hot material rises from deeper in the mantle. In simple terms, volcanoes tend to appear where the planet has natural pathways that allow heat and molten rock to move upward. They are not scattered randomly, but are closely connected to the deep structure and movement of Earth itself. Divergent plate boundaries often create volcanoes because the plates move away from each other and leave space for magma to rise. As the crust stretches and thins, pressure on the hot material below is reduced, and that makes melting easier. The magma can then move upward through cracks and weak zones. This kind of volcanism is especially important beneath the oceans, where it helps build new seafloor. Convergent plate boundaries commonly produce volcanoes when one plate sinks beneath another and helps generate magma. The descending plate carries water-rich minerals downward, and that water lowers the melting temperature of rocks above it. This makes magma generation more likely in the mantle above the sinking slab. Over time, chains of volcanoes can form above these zones and create some of the world's most dramatic volcanic landscapes. Some volcanoes form far from plate boundaries above mantle plumes, which are often called hotspots. These are areas where very hot material rises from deep inside the Earth and melts rock near the surface. As a tectonic plate slowly moves across a hotspot, it can leave behind a chain of volcanoes, with older ones farther away and younger ones closer to the present hotspot location. This is one reason volcanic islands can line up in long, graceful chains. Volcanoes that form at hotspots are not created by subduction, and they often produce different styles of magma, landforms, and eruption behavior. Instead of the steep, explosive cones often seen at subduction zones, hotspot volcanoes may build broad shield volcanoes from repeated outpourings of fluid lava. The contrast helps scientists understand that not all volcanoes are born from the same deep process. The planet has more than one way of creating fire at the surface. A volcano is, at its most basic level, an opening in Earth's crust through which molten rock, gases, and fragments of rock can reach the surface. That opening may be a summit crater, a side vent, or even a long crack in the ground. What matters is that it connects the deep interior to the outer world. A volcano is therefore not only a mountain shape, but also a functioning pathway for Earth's internal heat and material. Magma is called magma while it remains underground, but once it reaches the surface, it is called lava. This changing name is simple, but it helps distinguish between molten rock still under pressure inside the Earth and molten rock exposed to open air or water. Underground magma may still contain many dissolved gases, while lava at the surface begins cooling, flowing, and releasing those gases more freely. The difference is partly about location and partly about behavior. Shield volcanoes are broad and gently sloping because they are built mainly by many eruptions of fluid lava that travel far before cooling. Instead of piling up in steep layers near the vent, the lava spreads outward over large distances. Over time, these repeated flows create a wide, low-angle mountain that looks almost like a warrior's shield laid on the ground. Their size can become enormous, even if their slopes feel gradual. Stratovolcanoes, also called composite volcanoes, are usually steeper because they are built from alternating layers of lava, ash, and other erupted material. Some eruptions add lava flows, while others scatter loose fragments that settle around the cone. As this process repeats over long periods, the mountain becomes taller and more layered. These volcanoes are often the classic cone-shaped mountains that many people picture first. Cinder cones are relatively small volcanoes built mostly from loose pyroclastic fragments that fall back around a vent. Instead of being formed by long rivers of lava, they often grow from bursts that toss pieces of molten or partly molten material into the air. Those fragments cool and pile up close to where they landed, gradually creating a steep cone. They may be smaller than other volcanic types, but they can form surprisingly quickly. Calderas are large depressions that can form when a magma chamber is partly emptied and the ground above it collapses inward. This means the volcano does not simply blast outward. Sometimes it also drops downward when underground support is reduced. The result can be a vast basin-like feature, much larger than a normal crater. Some calderas later fill with lakes, host new vents, or become homes for entire communities. A lava dome forms when thick, sticky lava rises to the surface, but does not flow very far away from the vent. Because the lava is so viscous, it tends to pile up near the opening rather than spreading out. Over time, it can build a rounded mound or dome-shaped mass. These domes may look solid and quiet, but they can be unstable and important in more explosive volcanic systems. Fissure eruptions happen when lava erupts from long cracks in the ground instead of from one central crater. Rather than a single fountain at a summit, molten rock may emerge along a stretched line across the landscape. This can create curtains of fire and long lava flows that reshape wide areas. Fissure eruptions show that a volcano is not always a neat, isolated cone. A volcanic field may contain many vents spread across an area instead of one dominant volcano. In such regions, eruptions can break out from different points over time, sometimes producing cones, lava flows, and scattered vents across the same broader landscape. This makes volcanic hazards more complex because future eruptions may not come from the most obvious hill. The field as a whole is the volcanic system, not only a single summit. Some volcanic eruptions open new vents on the flanks of a volcano rather than erupting from the summit. This happens when magma finds weakness on the sides of the mountain and escapes there instead. Such eruptions can be especially important because they may begin closer to settlements, roads, or farmland than the main crater. A volcano's most dangerous opening is not always at the top. Rift zones are long, stretched regions on a volcano where magma repeatedly breaks through along cracks. These zones often mark structural weaknesses where the volcanic edifice pulls apart slightly and allows molten rock to rise. Over time, they can become key pathways for repeated eruptions. On some volcanoes, understanding the rift zones is essential for understanding where future lava may appear. Flank eruptions can be especially disruptive because they may occur closer to communities than eruptions at the summit. A summit eruption may be distant and elevated, but a side eruption can open lower on the volcano where human activity is concentrated. This changes both the travel paths of lava and the time available for response. The location of an eruption can matter just as much as its size. Magma chambers are not always single giant empty caves filled with liquid rock. In many cases, they are more like complicated networks made of meltriche zones, crystals, partly molten rock, and pathways of moving magma. This makes volcanic systems much more complex than simple diagrams often suggest. Beneath a volcano, the plumbing may be layered, uneven, and constantly changing. Magma can stall in the crust for long periods before erupting. During that time, it may cool somewhat, crystallize, change composition, or interact with surrounding rock. This pause can strongly influence what the eventual eruption looks like. A volcano's future behavior is often shaped by long underground waiting periods that no one at the surface can directly see. As magma cools underground, crystals begin to form within it, and this changes the composition of the melt that remains. Some minerals crystallize earlier than others, removing certain elements from the liquid and leaving the rest behind in a different balance. Over time, this can make the remaining magma more silica-rich, more viscous, or more gas-trapping. In this way, cooling does not simply make magma colder, it can make it chemically different. Magma mixing can happen when two different magmas come into contact inside the same volcanic system. A hotter, more fluid magma may rise into a cooler, stickier magma body, and the interaction can change temperature, gas release, and chemistry. In some cases, this mixing may help trigger an eruption. Volcanoes are not always powered by one simple liquid, but sometimes by interaction between multiple batches of magma. Assimilation happens when magma melts and absorbs some of the surrounding rock through which it moves. As it rises, it may not stay chemically pure, because pieces of the crust around it can become incorporated into the molten material. This process can alter the magma's composition and therefore influence how it behaves. The journey upward can transform magma as much as its source deep below. These underground processes, stalling, crystallizing, mixing, and assimilation can strongly affect how explosive or fluid an eventual eruption becomes. A magma that changes underground may erupt very differently from the magma that first began its journey. This is why volcanoes are often difficult to predict with precision. What happens below the surface matters deeply to what the world sees above it. Low-viscosity magma tends to erupt more quietly because gases can escape from it more easily. Since the magma is more fluid, bubbles can move through it and release pressure without building up as much resistance. This often leads to flowing lava, fountains, or gentler styles of eruption compared with highly explosive blasts. The stickiness of magma is one of the most important controls on volcanic behavior. High-viscosity magma tends to erupt more explosively because gases remain trapped inside it until pressure grows very large. Imagine the difference between gas escaping from water and gas trapped inside thick paste. In very sticky magma, the bubbles cannot move out easily, so pressure builds until the material can fragment violently. This is one reason some volcanoes explode with ash-rich force while others mostly pour lava. Basaltic magma is usually less sticky than rhyolitic magma. It generally contains less silica and often stays hotter, which helps it flow more easily. Because of this, basaltic eruptions are often associated with long lava flows, lava fountains, and shield volcanoes. Its relative fluidity gives many basaltic volcanic landscapes their broad, layered appearance. Rhyolitic magma is usually richer in silica and much more viscous than basaltic magma. That high silica content helps make the magma thicker, which means gases are more easily trapped inside. As a result, rhyolitic eruptions can be especially explosive and can produce large ash plumes, pumice, and powerful pyroclastic activity. The same molten rock can behave very differently depending on its composition. Andesitic magma has properties between basaltic and rhyolitic magma. It is generally more viscous than basaltic magma, but less viscous than rhyolitic magma, and its eruptions can range from moderate lava emissions to explosive ash-producing events. Many stratovolcanoes are associated with andesitic compositions. It often represents a middle ground in volcanic behavior. Dissolved gases in magma commonly include water vapor, carbon dioxide, and sulfur dioxide. While the molten rock itself is important, these invisible gases are often the real drivers of eruption style. As magma rises and pressure decreases, the gases come out of solution and form bubbles. Those bubbles can quietly escape or help power violent fragmentation. Water vapor is usually the most abundant gas released during volcanic eruptions. This may surprise people because they often think first of sulfur or toxic gases, but water is usually the main volcanic gas by volume. Much of it comes from the magma itself, though some may also come from groundwater heated by volcanic systems. Even so, the smaller amounts of other gases can still have major environmental effects. Gas pressure is one of the main reasons eruptions can become explosive. As magma rises toward the surface, the pressure above it drops, allowing dissolved gases to expand into bubbles. If those bubbles cannot escape easily, they keep expanding and increase internal pressure. At a certain point, the magma can break apart violently into ash, pumice, and fast-moving volcanic clouds. A volcanic plume can rise many kilometers into the atmosphere if an eruption is strong enough. The upward force comes from the energy of the eruption and from the buoyancy of hot gases and particles. Once the plume reaches higher atmospheric levels, winds can spread ash over very large distances. This is one reason eruptions can affect places far beyond the immediate slopes of a volcano. Fine ash from an eruption can travel far downwind and affect areas hundreds or even thousands of kilometers away. The smallest particles are light enough to stay suspended in the air for long periods, especially when eruption columns reach great heights. Because of this, a volcano can disturb transportation, water supplies, or air quality, far from the vent itself. The map of volcanic impact is often much larger than the mounting. The majority of Earth's volcanic activity happens beneath the ocean, and that underwater volcanism plays a major role in shaping the planet. Seafloor eruptions build new crust, create submarine mountains, and influence ocean chemistry and circulation in subtle ways. Even though people rarely witness them directly, they are among the most important geological processes on Earth. A great deal of the planet's growth happens out of sight below the waves. High water pressure changes the way submarine eruptions behave compared with eruptions in open air. Under deep water, pressure can suppress some gas expansion and alter how lava cools and fragments. This means an underwater eruption may look very different from a land eruption even when the magma is similar. The surrounding environment strongly shapes volcanic expression. Submarine volcanoes can build seamounts that may eventually grow into islands if eruptions continue long enough. Layer by layer, lava and volcanic debris accumulate on the sea floor until the structure rises toward the surface. If enough material is added, the volcano can eventually emerge above sea level and begin a new stage of erosion, ecology, and landscape development. Some islands begin in total darkness at the bottom of the sea. The island of Surtsey formed off Iceland during eruptions that began in November 1963. This made it one of the rare modern examples of a brand new volcanic island appearing in historical time. Because scientists were able to observe it from its beginning, Surtsey became extremely valuable for understanding both volcanism and ecological colonization. It was like watching fresh earth being made. Surtsey gave scientists a rare chance to study how life colonizes a newly formed volcanic island. At first, the island was mostly bare rock and ash, but over time, wind, waves, birds, microbes, and plants began to transform it. This made Surtsey a natural laboratory for understanding the earliest stages of ecosystem development. It showed how life can gradually arrive even in a place born from fire. Another short-lived Icelandic volcanic island called Jolnir formed during the same eruption sequence that created Surtsey, but it was later worn away by erosion. This shows that volcanic birth does not guarantee long-term survival. New land can appear dramatically and then vanish again under the work of waves and weather. Volcanic landscapes are often temporary, especially where the sea is constantly attacking them. Volcanic islands are temporary on geologic timescales because waves, landslides, and erosion continually reshape them. Even after their eruptions stop, the forces of water, wind, and gravity keep changing their size and form. Some islands shrink, collapse in parts, or become deeply carved by erosion. Their beauty often hides how unstable and short-lived they can be in Earth's long history. Some old volcanic islands eventually sink as the oceanic crust beneath them cools and slowly subsides. The volcanic edifice may remain, but the underlying plate grows denser and lower over time. This means an island can gradually descend, even without being destroyed all at once. The movement is slow, but over millions of years it can completely change the map. Coral reefs can sometimes grow around subsiding volcanic islands and later form atolls. As the island sinks, the reef may continue growing upward toward sunlight near the ocean surface. Eventually, the central volcano may disappear below sea level, leaving a ring-shaped reef and lagoon. In this way, volcanism can indirectly create one of the most peaceful-looking tropical landforms on Earth. Many mountain chains that are no longer volcanically active were built partly by ancient volcanism. Even when eruptions have long ceased, their rocks, intrusions, and old volcanic layers remain as part of the landscape. Over time, erosion may soften or expose them until the volcanic origin is less obvious. Much of what now looks like ordinary mountain country has a fiery past. A volcano's shape reflects the balance between lava flows, explosive eruptions, collapse, and erosion over time. No volcanic mountain is shaped by just one event. Instead, it is the result of many episodes, each adding, removing, or reshaping material. The cone, ridge, crater, or caldera we see is really a long history written into landform. Erosion can deeply modify old volcanoes and expose their internal structure. Rain, rivers, glaciers, landslides, and weathering can cut away the outer layers and reveal the rock pathways that once fed eruptions. This means some ancient volcanic regions display their inner plumbing more clearly than active volcanoes do. Time can peel the mountain open. A volcanic plug forms when magma hardens inside a vent, and the softer rock around it later erodes away. What remains is a resistant core that once sat inside the heart of a volcano. Such features can stand out dramatically in the landscape because they resist erosion better than surrounding material. They are like the solidified throat of a long-dead volcanic system. Dikes are sheet-like intrusions that cut across older rock layers and often mark pathways where magma once moved. They form when molten rock forces its way through cracks and then cools underground. After erosion removes softer surrounding material, dikes can become visible as walls or ridges in the landscape. They are frozen evidence of magma choosing a path upward. Sills are also sheet-like intrusions, but unlike dikes, they spread between existing layers of rock instead of cutting across them. This happens when magma finds a horizontal weakness and pushes its way sideways. As it cools, it forms a flat or gently curved body inside the crust. Sills show that magma does not always rise straight upward. Sometimes it spreads quietly within the earth. Laccoliths are intrusive bodies that push overlying rock upward into a dome shape. They form when magma intrudes between layers but is thick enough to lift the layers above instead of flowing widely. The result is a bulging structure produced from below. These features remind us that volcanic processes are not only about eruption, but also about slow underground construction. Not all volcanic activity reaches the surface. Much of it remains underground as intrusive rock, where magma cools and hardens within the crust instead of erupting as lava or ash. This hidden side of volcanism is extremely important because it builds large bodies of rock and shapes the crust from within. What erupts is only part of the full volcanic story. Subduction adds water-rich material to the mantle above the sinking slab, helping rocks melt at lower temperatures. This is one of the main reasons subduction zones are so productive volcanically. Water changes the behavior of hot mantle rock and makes melt generation easier than it would be in dry conditions. In a sense, water carried deep into Earth helps light the volcanic fires above. The Campi Flegrei region in Italy includes many vents spread across a large caldera area rather than one simple volcanic cone. It is a reminder that some volcanic systems are broad and complex, with activity distributed across a landscape instead of centered on one mountain. This makes them especially interesting and potentially difficult to interpret. The volcano is the whole region, not a single peak. In 1538, the Campi Flegrei area produced Monte Nuovo, a new cone that grew during a week-long eruption. This event was observed in historical time and showed clearly that entirely new volcanic landforms can appear quickly. A landscape that seemed familiar can change dramatically in only a few days. Volcanoes are capable of building new topography almost as suddenly as they destroy it. The Volcanic Explosivity Index, or VEE, is a scale scientists use to compare eruptions by looking at how much material they eject and how high their eruption columns rise. It is not exactly the same as measuring temperature or lava speed. Instead, it gives a broad sense of how large and explosive an eruption was. This helps people compare very different volcanic events in a more organized way, from relatively small eruptions to extremely powerful ones. Volcanic ash is not like the soft grey ash left behind after wood burns in a fireplace. It is made of tiny, sharp fragments of rock, minerals, and volcanic glass, created when magma and rock are broken apart during eruption. Because the particles are hard-edged and abrasive, ash can be far more dangerous than its gentle name suggests. Under a microscope, it looks more like crushed glass than soft dust. Even a thin layer of volcanic ash can damage machinery because those tiny particles are abrasive. When ash gets into engines, vents, filters, and moving metal parts, it can grind surfaces down over time. This is why ash is a serious problem for vehicles, power systems, and industrial equipment. A small amount may not look dramatic, but it can still cause costly and widespread damage. Volcanic bombs are blobs or blocks of volcanic material large enough to be thrown from a volcano while still hot or partly molten. Some take shape while flying through the air, stretching or spinning before they land. Others are more solid chunks blasted out by force. Even though the name sounds dramatic, it is simply a scientific term for large erupted fragments. Lapilli are volcanic fragments that fall in the size range between ash and larger volcanic bombs. They are bigger than fine ash grains, but smaller than the large chunks most people imagine during an eruption. Lapilli may be bits of rock, pumice, or molten droplets that cooled in the air. Their size affects how far they travel and where they settle around a volcano. Tephra is a broad word used for all airborne material ejected during an eruption, no matter its size. That includes fine ash, lapilli, and larger fragments. Scientists use this single term when they want to describe erupted particles without focusing only on one size category. It is a useful way of talking about everything that is blasted into the air and later falls back to the ground. Pyroclastic flows are fast-moving, ground-hugging currents made of hot gas, ash, and broken volcanic rock. They move down the slopes of a volcano instead of rising like a normal plume. Because they are extremely hot, dense, and fast, they are among the most dangerous volcanic events known. They can overwhelm landscapes in a very short time. Pyroclastic flows can move at speeds that make them one of the deadliest volcanic hazards on Earth. Their heat alone is extreme, but their speed means there is often little or no chance to outrun them once they are on the move. They can race through valleys and across slopes while carrying ash and debris in a thick, turbulent current. This combination of speed, heat, and force makes them especially destructive. Pyroclastic surges are closely related to pyroclastic flows, but they are generally more dilute and turbulent. Because they contain less dense material, they can spread in a more flexible way and move over obstacles more easily than denser flows. That makes them difficult to predict in detail. Even though they may be lighter than pyroclastic flows, they are still highly dangerous. Lahars are fast-moving mixtures of water and volcanic debris that flow down valleys like wet concrete. They can contain ash, mud, rock fragments, and water in a heavy, rushing mass. What makes them especially important is that they follow river channels and low ground, sometimes far from the volcano itself. In many regions, they are one of the most serious long-distance hazards. Lahars can happen during an eruption, right after one, or long afterward, if rainfall remobilizes loose volcanic ash and debris. This means the danger does not always end when the eruption does. A volcano can leave unstable material on its slopes, and later storms can set that material in motion. In this way, past eruptions can continue causing hazards months or even years later. Lava flows rarely kill large numbers of people directly because they usually move slowly enough for evacuation to happen. In many cases, people can leave on foot or by vehicle well before the lava arrives. This makes lava visually dramatic, but often less deadly than faster volcanic hazards. Still, its slow pace should not be mistaken for harmlessness. Lava can still destroy roads, buildings, farmland, and utility systems, even when people escape safely. A moving lava flow can bury neighborhoods, cut transportation routes, sever pipelines, and reshape the ground itself. The damage may be total and permanent in the path it covers. So, while lava often allows time for people to flee, it can still erase the built environment. Volcanic lightning can occur inside ash plumes because repeated collisions among ash particles help build up electrical charge. In a way, the ash cloud behaves like a giant storm cloud, but one made partly from fragmented rock and glass. When the charge difference becomes large enough, lightning flashes through the plume. It is one of the most striking examples of how eruption columns create their own intense atmospheric behavior. Steam blast eruptions can happen when water is suddenly heated by hot rock or magma. If groundwater or surface water comes into contact with something extremely hot, it can flash into steam with violent force. In these cases, the energy comes mainly from rapid heating and expansion of water rather than from fresh magma being erupted directly. That makes these eruptions a special kind of volcanic hazard. Steam-driven eruptions may happen with less warning than magma-driven eruptions. Because they can be triggered by hot rock interacting with water near the surface, they do not always require large amounts of new magma rising first. This can make them harder to forecast clearly. A volcano that seems relatively quiet may still produce a sudden steam explosion under the right conditions. Small earthquakes beneath a volcano can indicate rock cracking or magma movement underground. As magma pushes its way upward or shifts within the crust, it may break surrounding rock and create seismic signals. Scientists pay close attention to these swarms because they can provide important clues about changing conditions below. The ground may begin whispering before the volcano speaks loudly. Many volcanoes show warning signs before erupting, including earthquakes, swelling of the ground, and changes in gas output. None of these signs guarantees an eruption by itself, but together they can reveal that the system is becoming more active. These changes help scientists track pressure, magma movement, and heat beneath the surface. Volcanoes often give hints, though not always in a simple way. Volcano monitoring often combines seismometers, GPS instruments, satellite measurements, gas sensors, and direct visual observations. No single method tells the whole story, so scientists use several tools at once. One instrument may detect earthquakes, another may measure swelling, and another may track gas changes. Together, these methods create a fuller picture of what the volcano is doing. GPS networks can detect tiny changes in ground position caused by magma accumulating underground. The movement may be too small for people to notice, but high-precision instruments can measure the ground rising, sinking, or shifting by very small amounts. This is important because swelling can suggest that magma is building pressure beneath the surface. A volcano may subtly inflate before it erupts. Satellite radar can measure ground deformation across large volcanic regions without instruments being placed everywhere on the ground. By comparing radar images taken at different times, scientists can detect small changes in elevation or surface shape. This is especially useful in remote or dangerous areas where direct access is difficult. From space, it becomes possible to watch the land slowly breathe. Thermal imaging helps scientists detect changes in surface temperature at active volcanic sites. Hot cracks, lava, new vents, and warming ground can all show up clearly in thermal data, even when they are hard to see with the eye. This can reveal changes that happen at night or through light cloud. Heat often leaves a visible signature before or during volcanic activity. Gas monitoring instruments can measure sulfur dioxide, carbon dioxide, hydrogen sulfide, and water vapor near volcanoes. These gases tell scientists about what is happening in the magma below and in the hydrothermal system above it. A sudden increase or change in the gas mix can suggest that magma is rising or that pressure is changing underground. In many cases, gas is one of the earliest signals of unrest. Scientists also study a volcano's past eruptions because its history helps estimate what kinds of future activity are possible. The layers of ash, lava, and debris around a volcano act like a long matral archive. By examining those records, researchers learn whether the volcano usually produces lava flows, explosive ash eruptions, lahars, or long, quiet intervals. The past does not predict everything, but it gives valuable clues. Volcano observatories issue notices and alert levels to help officials and the public respond to changing activity. These systems are designed to turn complex scientific observations into practical information that people can act on. A change in alert level may influence evacuations, aviation decisions, road closures, or emergency planning. Good communication is as important as good measurement. Monitoring networks are especially important in places where people live close to active volcanoes. In such regions, even a modest increase in warning time can save lives and reduce confusion. A monitored volcano is not less dangerous, but it is better understood. That understanding helps communities prepare more calmly and effectively. Volcanic gases can harm vegetation, buildings, and human health, even when no major eruption is taking place. Gas emissions may continue quietly from vents, fissures, soils, and fumaroles for long periods. Some gases irritate eyes and lungs, while others affect crops, metals, or water chemistry. The hazards of a volcano are not limited to dramatic eruptions. Sulfur dioxide released by volcanoes can react in the atmosphere to form acidic aerosols. These tiny droplets can spread in the air and affect visibility, breathing comfort, and atmospheric chemistry. They are also important for climate because, in large eruptions, they can reflect sunlight. A gas released from the volcano can therefore continue changing the environment long after it leaves the vent. Hydrogen fluoride from volcanic emissions can dissolve into water droplets and contribute to acid deposition. Even in small amounts, fluoride can be significant because it affects water, plants, and animals. In some eruptions, it has caused serious agricultural and livestock problems. This is one reason volcanic gas chemistry matters so much beyond the volcano itself. Carbon dioxide from volcanoes can collect in low-lying areas because it is heavier than normal air. If it accumulates in hollows, valleys, or enclosed spaces, it can displace breathable oxygen. That makes it dangerous even though it is invisible and has no dramatic color. Some volcanic hazards arrive silently rather than explosively. In rare cases, volcanic gas can be dangerous even without lava or ash if it gathers in enclosed or poorly ventilated terrain. People and animals can be overcome simply by entering an area where oxygen has been pushed aside by volcanic gases. This kind of hazard can be especially deceptive because the landscape may appear calm. A still place can still be unsafe. Vogue is a haze formed when volcanic gases and tiny particles react in the atmosphere. The word comes from combining volcanic and smog. It can spread over broad areas downwind from an active volcano, and sometimes linger depending on weather conditions. Even without ashfall, a volcano can affect the air people breathe. Fog can reduce visibility and irritate the eyes and lungs. For people with asthma or other respiratory conditions, it can be especially uncomfortable. It may also affect outdoor activity, transportation, and daily life in areas near active gas emissions. A volcano can therefore influence communities even during quieter phases of activity. Ashfall can contaminate water supplies by adding fine particles and changing water chemistry. Reservoirs, rooftop collection systems, streams, and treatment facilities can all be affected. The particles may clog systems or make water more difficult to clean. This is one reason ashfall becomes a public health and infrastructure issue very quickly. Wet ash is much heavier than dry ash and can collapse roofs. When ash becomes soaked by rain or moisture, its weight increases sharply, and buildings not designed for that load may fail. This means even moderate ashfall can become much more dangerous during wet weather. The same ash can behave very differently depending on conditions after it lands. Ash can short-circuit electrical equipment and interfere with communication systems. Fine particles can settle into exposed components, insulators, and transmission equipment, causing faults or outages. This can make emergency response harder at the very moment it is most needed. The effect of ash is often technical and widespread, not only visible. Fine ash is especially dangerous to aircraft because it can damage engines and flight systems. At cruising altitude, aircraft may enter ash clouds they cannot easily see, especially at night or in bad weather. The particles can scratch surfaces, clog systems, and melt inside hot engines. This makes volcanic ash a major aviation concern around the world. Volcanic ash clouds can drift far from the source, turning aviation into a global volcanic issue rather than only a local one. A volcano in one country can affect air routes across entire regions if winds spread ash into major flight corridors. This is why ash monitoring depends on satellites, models, observatories, and international coordination. The sky can carry volcanic risk far beyond the mountain. Jet engines can lose power or even fail if they ingest concentrated volcanic ash. The ash can melt in the hot parts of the engine and then solidify again on turbine components, disrupting airflow and performance. This is one of the main reasons pilots and aviation authorities avoid ash clouds so carefully. The danger is not only abrasion, but also heat-related buildup inside the engines. Aviation authorities use ash advisories and specialized forecasting centers to keep aircraft away from dangerous plumes. These centers track volcanic activity, analyze weather patterns, and model how ash may spread through the atmosphere. Their work helps airlines reroute flights and reduce risk. In modern aviation, volcano science is part of everyday safety planning. The 2010 eruption of Eyjafjallajökull showed how even a moderate eruption can disrupt air traffic across a very large region. The eruption itself was not among the largest in history, yet its ash plume affected a busy airspace network across Europe. This event became a major lesson in how interconnected the modern world is. A single volcano can interrupt movement on a continental scale. Some of the busiest flight routes in the world pass near volcanic regions, especially in the North Pacific. Because of that, eruptions in places such as Alaska or the Aleutians can matter enormously for international aviation. Even remote volcanoes can become globally important if they send ash into major air corridors. Geography and transportation together shape the risk. Vesicles are gas bubbles frozen into volcanic rock as lava cools. When molten rock contains dissolved gas and then solidifies before all the gas escapes, holes are left behind in the rock. These cavities preserve the memory of bubbling inside the lava. They are a small-scale record of how gases behaved during cooling. Scoria is a vesicular volcanic rock full of holes left behind by escaping gas. It is often dark, rough, and lightweight compared with denser volcanic rocks, though it usually does not float like pumice. Its texture tells the story of gas-rich lava that cooled after frothing. In many cinder cones, scoria is one of the main building materials. Pumice is so full of bubbles that some pieces can float on water. This happens because the rock contains so many tiny trapped gas spaces that its overall density becomes very low. It may look like stone, but it can behave strangely compared with ordinary rock. Pumice is one of the clearest examples of how gas changes volcanic material. Floating pumice rafts can travel long distances across the ocean after large eruptions. Carried by waves and currents, these rafts may drift for months and cover broad areas of sea. They are unusual reminders that an eruption can produce material light enough to move like a floating field. Even solid rock can briefly join the surface of the water. Obsidian is volcanic glass formed when lava cools so quickly, but crystals do not have time to grow. Instead of becoming a typical crystalline rock, the molten material hardens into a smooth, glassy substance. Its sharp edges and shiny appearance make it very distinctive. Obsidian shows how cooling speed can completely change the texture of volcanic rock. Perlite is another volcanic glass, but unlike obsidian, it contains water and can expand greatly when heated. When processed, it puffs up into a lightweight material used in construction and horticulture. Its unusual behavior comes from the water trapped within its structure. This is a good reminder that volcanic materials often have important uses beyond geology. Tuff is rock formed from volcanic ash that has settled and then become compacted or cemented together over time. What begins as loose erupted particles can gradually harden into solid stone. Tuff often preserves clues about eruction style, ash composition, and the environment where the material was deposited. It is loose volcanic fallout transformed into rock. Ignimbrite is rock deposited by hot pyroclastic flows. Because those flows move as dense, fast currents of hot ash and debris, the deposits they leave can be thick, widespread, and distinctive. Studying ignimbrite helps scientists understand some of the most powerful explosive eruptions. It is the hardened footprint of a moving volcanic cloud. Welded tuff forms when hot volcanic fragments land while still hot enough to stick together and fuse. Instead of cooling as loose ash and pumice, the material partly softens and presses into a more solid mass under its own heat and weight. This gives the rock a compacted, sometimes flattened look, especially where hot fragments were squeezed together. It is a reminder that some volcanic deposits are still changing even after they hit the ground. Columnar joints can form in cooling lava when the rock contracts and cracks into repeating polygonal columns. As the lava loses heat, it shrinks, and that shrinking creates stress inside the solidifying rock. The stress is released through cracking, often in a surprisingly organized pattern. What looks like careful stone architecture is often just the geometry of cooling. Basalt commonly develops columnar jointing when thick lava flows cool slowly enough to crack in a systematic way. The slower and more even the cooling, the more orderly those columns may become. That is why some basalt landscapes show striking natural pillars that seem almost artificial. Their shape is really the frozen record of heat leaving the rock. Volcanic glass weathers differently from crystalline rock and can change rapidly under some conditions. Because it lacks an orderly crystal structure, it may break down more easily when exposed to water, chemical reactions, and time. This means a rock formed very suddenly can also alter fairly quickly once it is exposed at the surface. the same rapid cooling that creates glass can make it less stable later. Fresh volcanic deposits often look barren at first, but they can become important places for ecological succession. In the beginning, the surface may seem lifeless, with only ash, lava, and broken rock. But over time, wind, water, microbes, and living organisms begin transforming that raw ground. A volcanic landscape can become a stage for life to begin again. Pioneer organisms such as microbes, lichens, and mosses are often among the first living things to colonize new volcanic surfaces. These organisms do not need thick soil or large amounts of organic matter to begin growing. They can settle into cracks, trap moisture, and slowly help break rock down further. Their quiet arrival is often the first step in turning bare volcanic ground into an ecosystem. Over time, weathering breaks volcanic rock into mineral-rich soil. Rain, temperature changes, plant roots, and chemical reactions slowly wear down the rock into smaller particles. As that material mixes with organic matter from living things, it becomes more supportive of plant life. What begins as hard lava can, over long periods, become productive earth. Volcanic soils can become very fertile, which is one important reason so many people live near active volcanoes. Minerals released from weathered volcanic material can support strong plant growth when conditions are right. This creates a difficult balance, because the same land that offers rich farming potential may also carry real volcanic risk. Human settlement often follows both danger and opportunity. Fertile volcanic regions support major agriculture in places such as Indonesia, Italy, Japan, Mexico, and many other parts of the world. Farmers in these regions may benefit from soil that has been enriched over generations by weathered ash and lava. Crops can grow well in these mineral-rich environments, supporting large populations. In this way, volcanoes help feed people even while they remain natural hazards. The same volcano that threatens crops during eruptions may improve soil productivity in the quiet years between eruptions. Ashfall can destroy a growing season, but over longer timescales, weathered volcanic material can enrich the land. This creates one of the most interesting contradictions of volcanic regions. A volcano can be both a destroyer of harvests and a long-term supporter of agriculture. Volcanic ash can initially damage farmland, but over longer timescales it can improve soil as it breaks down and releases minerals. In the short term, ash may smother leaves, bury crops, and disrupt water systems. But once weathering takes over, that same material can contribute nutrients and better soil structure. Time changes the meaning of volcanic deposits. Some volcanic minerals are mined for industrial use, including sulfur, pumice, and pozzolanic ash. These materials may be valuable because of their chemical properties, lightweight, abrasiveness, or usefulness in construction. Volcanic terrain is not just geologically interesting, it can also supply important resources. Human industry often finds practical value in erupted material. Ancient Romans used volcanic ash in concrete, and some of that concrete has shown remarkable durability over very long periods. The ash helped the mixture react in ways that made it strong and resilient, especially in marine settings. This ancient knowledge turned volcanic material into a building advantage. A product of eruption became part of one of history's most famous construction traditions. Pozzolana, a volcanic ash used in Roman construction, reacts with lime and water to form strong cement-like material. This chemical reaction allows the mixture to harden and gain durability in a way that ordinary simple mud or mortar cannot. It is one of the classic examples of how volcanic material can be useful far beyond its original eruption. A cloud of ash can become part of an enduring wall or harbor. Geothermal energy is often accessible in volcanic regions because heat remains close to the surface there. Groundwater can be heated by hot rock deep below and then tapped for heating or electricity. This allows people to use volcanic heat as a practical energy resource instead of viewing it only as a hazard. In some places, the Earth's warmth becomes part of everyday infrastructure. Iceland uses geothermal resources associated with its volcanic setting for heating and electricity. Its unusual position over both a hotspot and a plate boundary gives it abundant underground heat, close enough to be useful. As a result, volcanism in Iceland is not only something to monitor, but also something to live with and benefit from directly. The same geologic forces that create eruptions also help power homes. Volcanic landscapes often host hot springs, fumaroles, and geysers where underground heat interacts with water. These features show that a volcano does not need to erupt lava to reveal its presence. Heat can circulate quietly through rock and groundwater, producing steaming vents, boiling pools, and mineral-rich waters. They are softer surface expressions of the same deep energy. A fumarole is a vent that emits steam and volcanic gases. It may not produce lava or dramatic explosions, yet it still marks a place where heat and gases from below are reaching the surface. Fumaroles can appear along crater walls, lava fields, and geothermal areas. They are quiet breathing points of an active volcanic system. Solfataras are fumaroles, especially rich in sulfur gases. Because of the gases they release, they often create strong smells and colorful mineral deposits around the vent. Yellow sulfur may collect nearby, and the surrounding rock can become chemically altered. They are a vivid reminder that volcanic activity is not only about molten rock, but also about reactive gases. Mud pots form where acidic hot water breaks down surrounding rock into clay. The mixture of water, heat, gas, and altered minerals creates bubbling pools of mud instead of clear hot springs. These features are often found in geothermal areas where volcanic heat remains near the surface. They show how underground chemistry can reshape rock into something soft and fluid. Geysers are not volcanoes themselves, but they often occur in volcanic regions with abundant heat and groundwater. A geyser needs a special underground plumbing system that traps water, heats it, and then suddenly releases it upward as steam and hot water. So while geysers and volcanoes are different things, they often share the same deep heat source. They are cousins in the same geothermal family. The collapse that forms a caldera can happen because the support above a partly emptied magma reservoir is lost. When enough magma is removed during an eruption, the rock overhead may no longer be fully supported and can sink or break downward. This means a caldera is often a collapse feature, rather than simply a crater blasted out by force. The volcano can fall inward as much as it erupts outward. Calderas can later contain lakes, lava domes, renewed eruptions, or even towns and cities. After the collapse, the landscape does not stay frozen in one stage. Water may fill the depression, new volcanic activity may return, or people may settle on or around the altered terrain. A caldera is often the beginning of a new chapter in the volcanic story, not the end. Santorini is an example of a volcanic island group shaped by multiple caldera-forming events. Its present beauty, with steep cliffs and a flooded central basin, is tied directly to a long history of major eruptions and collapse. The land and sea layout seen there today is really a volcanic structure viewed after repeated transformation. A scenic island can be the remnant of immense violence in the past. The Santorini volcanic complex includes overlapping shield volcanoes capped by several calderas. This means the area was not built by one single event or one single cone, but by repeated phases of growth and collapse. Different volcanic structures were layered and then partly